Good evening. I would like to first of all, thank the organizers for allowing me to present this work over here. So I'll be talking about geometric origin of near criticality in multi-channel sensing. So here's the puzzle. So the puzzle is that criticality is pretty much ubiquitous in biology. You find it in the brain, at least there is a lot of evidence for that. You find it in gene regulatory networks, you find it in cellular systems, and it's all over the place in biology. So William Bialek actually started this question. He basically asked this question: if biological systems are near criticality, and criticality basically is a set of parameters, is a very fine-tuned set of points in the parameter space, how does a generic adaptive system should typically miss this particular point? But it always happens that it actually goes and tunes itself to these particular fine-tuned points. So there were several solutions which were given, and the solutions basically the most important ones are self-organized criticality and Griffith's phases. So I'll be giving another solution, but I'll also be addressing certain gaps in this particular solution which both self-organized criticality and Griffith's phases do not give. The gaps are: when does near criticality actually exist? What are the conditions for that? Why near criticality is generic, and why dynamics always ends up reaching the critical point. So first of all, I'll be doing this for a class of adaptive systems, which I call as, okay, first of all, let me define what an adaptive system is. Adaptive systems are non-equilibrium systems whose internal control parameters are endogenized, and they evolve so as to optimize some functional objective in changing environments. Putting it more mathematically, if a biological system is adaptive, it takes a signal A, it represents itself in terms of some internal representation psi A, it does some nonlinear computation with this function f, which is highly nonlinear, and then it updates itself according to the environment. A slightly more general form is that it takes a signal A, it represents itself in several such internal channels, and then it does a nonlinear computation on that. Now, this kind of a definition of adaptive systems subsumes even things like large language models and many other biological systems. Okay, so but now we're in a situation where we have a highly nonlinear function, and we want to go about a point where we can actually solve this particular problem, where we can have some kind of analytical handle over it. So what we do is, first of all, assume certain things. Assume that there is a mutual information function which corresponds to each of these channels and the updates, and that the total mutual information is basically conserved. And then I can put additional constraints on this, that the variance is basically a constant, and channel-wise projected variance is again conserved. With this, I can then write a variational form, and then I get, on maximizing this kind of Shannon entropy over here, I get these channels which are like very Gaussian in nature. And these Gaussian channels have this parameter k, which is basically the stiffness matrix, and then I can study the stiffness matrix and look at the eigenvalues of the stiffness matrix and go about finding criticality. So okay, so with this, so we now have a situation where this update is now becomes linear, and this can be written as sum over all these particular channels, where this B is basically a kind of a matrix now, and now I can do geometry with this. So here is a main result which I'll be doing. What I'll be showing at the end of the day is, if you have channels more than three channels, almost every trajectory satisfies this fact that it will end up in the t equal to infinity limit in a near critical state. Now, one thing I wanted to show was this. This stiffness matrix has this parameter lambda I plus some other matrix A beta I. This A beta I is a positive semi-definite matrix, and this lambda is basically a positive number. So K beta is strictly positive definite matrix. So in the limit of criticality, if the eigenvalues of A, minimum eigenvalue of this goes to 0, you still end up with some positive number, and this basically tells you is a noise flooring, so you can go very close to criticality but not achieve criticality. Okay, so what I'll be doing, if I can't even finish the talk, at least this part of the structure which I would like to explain. First of all, I'll be talking about the conditions for criticality. When can criticality occur? How does, if the system can actually absorb a certain amount of information? And then I will show that for M, when you have only one channel, you will find no criticality. And for more than, and for the critical set, which is their M crit, always has a dimension of M minus, has a dimensionality of N minus 2. That is the geometric thread of this theorem. And there is also a parallel, a dynamical thread, wherein which I will invoke some sort of a proxy function J, which is always non-increasing. I'll be proving that. And then I'll show the rank of the Hessian of this particular proxy function has one rank structure. So for channels more than 3, you have no trapping points in this particular landscape. And then I will show that this particular, the manifold of this budget is basically compact. You can define a kind of a Lyapunov function related to this minus of J, and then you'll find that in the t equal to infinity limit, using Lassalle's invariance process, your system will always go to criticality. So this is the full funneling theorem. Okay, so I will, obviously in the interest of time, I don't have much time, so I will go through this very intuitively as much as possible. So first of all, let's say you have some particular budget. In this particular M, if you have M channels, you have M Lagrange multipliers in that variational function. So you have like each of these budgets basically defines a particular manifold. Now, what this particular theorem says is that if you have a direction in the update space such that this the eigenvalues of this is 0, then what happens is you can basically separate the eigenspace of this into direction into channels which actually couple with this direction U and those which don't couple with this direction. U is the direction in which you have the soft mode. Now, if the budget is enough, if the budget is less than, now there's the total amount of channel capacity which it has. If your total budget is less than the channel capacity, the critical set is always existing. I mean, you always have it's a non-empty set. That's what this particular theorem says. The second theorem is pretty intuitive. You have this manifold, now you have an n-dimensional parameter space, and the manifold over here, because it has a single constraint of the budget, is m minus 1 dimensional. Now you have another manifold in the parameter space which corresponds to the 0 eigenvalue of the stiffness matrix. You have two m minus 1 dimensional surfaces intersecting, and they'll intersect in the m minus 2 dimensional thing. So what you have now is a condition that m minus 2 always has to be greater than or equal to 0. Okay, so now from this we can, what we already have is that, oops. So I forgot to say one more thing here. Now if you have only one single channel and you can't, you have 2 minutes, right? Yeah. So if you have only one single channel and you have a soft mode in that direction, you don't have any other channels to actually accommodate the rest of the information, you cannot have criticality. So at m equal to 1, you don't have criticality. For m equal to 2, as I said, the intersection is m minus 2 dimensional. You'll have fixed points. So system always has to fine tune itself to that particular point. And for m greater than or equal to 3, you'll always find criticality at the boundaries of the manifold. So that now let's go to the dynamics. Here I'm assuming that the system is near, most biological systems which adapt are near the information limited regime. There we can basically, let's say J is some sort of a proxy function, and then the susceptibility comes as 1 by lambda plus mu min, where lambda is your noise floor. Then what happens is that if you differentiate this parameters beta, the gradient which becomes a gradient of which is proportional to the gradient of J, it needs to be projected onto the manifold, because if it is away from the manifold, you will get out of the manifold and you will break the constraints. You can show that this J, dJ by dt is always greater than 0. Now just look at this, the minimum eigenvalue, if you fix all other betas, only change beta alpha, this is always positive. So the only way this J can change is by decreasing this mu min. So the moment the system wants to increase its response, it reallocates the information in such a way so that it starts decreasing the mu min. So it ends up actually going towards the critical point. Now this is the final thing, but it may go to the critical point, but what if there are traps in the critical point? So we can actually show that the Hessian structure is basically a positive semi-definite matrix minus a rank 1 matrix, which always tells you that the system can never have maximas in the system. So then by Lascelles invariance principle, any trajectory, all with there's only some measure zero trajectories in initial conditions which will not end up in this critical point. So by Lascelles invariance condition, you always end up in the critical curve. Okay. So with all these things, we can finally state that we have a geometry and we have defined when mcrit is non-empty. We have used this compactness lemma and Lascelles principle to show that the system for m greater than equal to 3 will never have interior critical points, and from Lascelles invariance theorem, you will always end up going to the critical curve. So this basically proves this basically is an explanation for all the proofs here. So what this work does not say is it does not establish the rate of convergence to the critical point. It does not identify which point in the critical curve the system will actually reach. And the funneling results requires that you're in the information limited regime. If you're in the amplification cost regime, you'll always end up in an interior maximum. What this work does say is that exact criticality is a wrong target. Near criticality is a geometric expectation of any adaptive system with 3 or more channels operating under fixed noise flow and conserved budget. Thank you very much.
Any questions?
Yes, that's what the stiffness matrix the allocation of the channel information will be such that it will keep decreasing the mu min. So even if mu min, which is the eigenvalue of A beta, goes to 0, you will really not reach 0 eigenvalue, you will reach 1 by lambda. So there is a fix over there. So you will go to near criticality, not exactly near criticality. Matrix columns are not independent of each other. The channel matrix, no. Which way? I'm sorry, which?
The 0 eigenvalues will mean that the rank is lower than the dimension, right?
Yes, so one of the eigenvalues becomes 0. One of the channel eigenvalues becomes 0 in order for you to.
I thought more than.
What?
I thought more than one should become 0.
I don't understand your question.
Are there any finite size effects here that you have considered? I mean, what is the size of these systems? Because as you get to the thermodynamic limit, you could come close to the transition.
It's just, let's say you take a single bacteria or a single LLM, you have just M channels.
This is like a dynamical phase transition that you're talking about?
This is a critical phase transition, that is the stiffness matrix basically goes to 0. So the distribution of this update is not normalizable in that direction.
I see. Okay.
If no more question, let's thank the speaker.
Thank you.